I'm Mariano Guerra. That's my Twitter handle. I'm the co-founder of InstaDeck. You can check it there. We use Erlang and FN in the backend. So we eat our own dog food. And this is a tour through the distributed system zoo. So the usual way I prepare talks is I think of a talk I would like to see or present if I knew about the things. And then I put a title that I find fun and write the abstract. And then I start thinking on how to actually fill the slides for that. And this one was hard. I think the problem is hard because I tried many ideas. And this is not advancing. Yeah. The first one was, which is in the abstract, which is, OK, I want to explore the different parts of the distributed system landscape. Let's do it like this. I will define a problem, and then let's see how all these algorithms and implementations and systems behave when solving this problem. Of course, you get the problem you can see in this comic that depending on the problem you define and the systems you're trying in that test, some may behave better just because the problem is suited for them. In my case, I decided to define the problem as a key-value store, which already makes some of the contenders better suited for it than others. But still, even if you define any test and the systems are different, because that's why you're trying to compare them, you learn something from, like, if you see that the monkey will have an advantage, it tells you something about the monkey and the other animals, that why he can solve the problem better than the others. But I thought about it, and I said, OK, let's try something different. If I have time, I can explain how each of these systems behave when trying to solve the key-value store problem. But I will leave it to the end, to the questions, or maybe to the hallway when I finish. So the second approach I tried is let's do the Gartner-style quadrant, which is let's put 2 dimensions, let's cross them, and chart the systems in the quadrant and see where they are placed, how they are placed related to similar system and different systems, and most interestingly, which holes are there in the quadrant. Like, where is a space where no system is, and what does this mean? Does it mean that it's impossible, or does it mean that it's not invented yet? For example, the memory store, which is a new electronic component, was found because there was an empty space in the solution space, and people said there should be something there, and they found it after like 30 years of trying. I could come with many dimensions, but crossing 2 didn't make any sense. This usually works. The reason why I tried this, why I tried to try this, was because with programming languages and databases, we can do this. Like, we do like object-oriented on one side and functional on the other, mutable and immutable, strongly typed, weakly typed, interpreted, compiled. And you can chart, and we can talk about languages in those terms. If you compare databases, you can say relational versus key-value store, one node, scalable, eventually consistent, many other categories. But trying to solve this for distributed systems, I couldn't come up with nice quadrants like this one, which is I found. The other one, since the title said zoo in it, which was I thought if I had to design a map of distributed system, but not any map, a map of a zoo, because each distributed system is an animal, that was the wrong idea to have. I'd say, well, if every distributed system is an animal, then you have like different species, and they evolve from each other. And let's write like a taxonomy of the evolution of distributed systems. There's an evolution, of course, but it's hard to make a tree out of it because some take ideas from the others, but not many are direct descendants from other ideas. So, and if I managed to do this, I wanted to do a Pokemon themed talk, but I couldn't. The third idea was not quadrants, but Venn diagrams, because the CAP theorem has a Venn diagram, and it's really easy to explain, or is. I think it's easy to explain CAP theorem in terms of the Venn diagram. And I have an animal theme Venn diagram, so I say if I can make a Venn diagram so cool as this one, then the talk will be nice. But it's similar to the quadrant, but even harder. I think it's harder to design good, meaningful Venn diagrams than to design quadrants. So after failing like 4 attempts at designing a talk, I think I found a way of presenting this. But this is an attempt to map the territory, and it's like Joe said today, it's an experiment. Because I think I will be wrong in many aspects of how I'm organizing this presentation, but I think it's really important for you to tell me where I'm wrong so I can improve this categorization and maybe change it. Or if you can present it in terms of the other things I said, that will be cool. We will all learn from it. So I've been told that I stretch analogies too far. This may be the case, so beware. So the story so far is distributed systems was not the beginning. The beginning was when there was no distributed system, which is a single thread operating on private data and no other thread of execution interfering with that. And even then, like, there was no concept of threads before threads, so it was just the CPU doing one thing at the time. Then something happened. In 1978, Leslie Lamport tried to make 2 organisms agree on a value. And this has made a lot of people very angry and being widely regarded as a bad move. But here we are because we cannot infinitely vertically scale systems. If we could run in an infinitely powerful computer, we will do in a single core. But we can't because one of the reasons is the speed of light. And so we have to make systems agree somehow. So now I will start with the categorization. The first group, or species, let's call it, is what I call the strong consensus group. And it has 2 kinds of systems for different levels of scale. The cluster systems, I call them, are started with an algorithm called view stamped replication in 1988. It was followed by a paper that was as obscure as maybe this talk, because it talked about an island in Greece where some democracy had to agree on the laws, and people for a while didn't understand what the paper was about. It was retried like 10 years later, and people kind of got the idea, and then like 20 years later, we realized that there was a consensus algorithm in those papers, and a consensus exploded. So we had, after that, Zookeeper Atomic Broadcast in 2011, which is being used in Zookeeper, the tool. And after that, if you read the Raft paper, they say that one of the reasons why they designed the Raft was because they couldn't understand Paxos. So that tells you something about Paxos. And I highly recommend you that if you're interested in reading papers about this, read Raft. It's the basic idea of Raft, and the title of the paper is a simple and easy to understand consensus algorithm, and it's quite approachable. These are systems that run in a small amount, depending on what you mean by small, between like 3 and below 100 number of nodes, and they run on a trusted environment. We will see why later. And then if you try to push the scalability of these systems, we got in 2008, you could consider that the seminal paper on the topic, the Bitcoin paper. But there's an article on ACM called Bitcoin Academic Pedigree that tells you which ideas Bitcoin took to define this, that we call now blockchain. And the problem is that since there's no standard definition of what blockchain is, it's really hard to know when all the parts of the blockchain were defined. So let's say that it was in the Bitcoin paper, but all the parts were there before. This paper just gets all the components and puts them together in a coherent way. These algorithms, since they need to scale, they use different consensus algorithms than the ones we saw previously. The most used now is proof of work. There are others called proof of stake, which is being explored, for example, in Ethereum. And there's another one that usually it's used in what's called permissioned blockchains, which are blockchains used in trusted environments, which is similar to consensus, so it's a gray area, which uses specialized hardware called SGX, an extension, for example, in the new Intel chips, that allows you to do something that's called proof of elapsed time. It's a way to say, okay, all of you have to sleep for a random amount of time, and then provide me a cryptographic proof that you slept for that time, and that's run on something called an enclave, which is made by hardware, and you cannot fake that. If I ask you to sleep for a random amount of time and provide me a proof, you cannot fake the fact that you slept for a random amount of time. The core ideas of this kind of system is there's a shared serialized operation log. The important part here is serialized. All the nodes in the system must apply the operations in the same order to arrive to the same state at the same point in time. So that's why strong consistency. If you have a cluster of consensus nodes, all will be moving like in lockstep. They will all get the next operation. They will either apply it or not, and then they will all move to the next state. These kind of systems are like the evolutionary pressure for this kind of system is about agreeing on a shared value. They are the way they are, and they have the properties they have because the core thing they provide is the fact that if you ask one node for a value, all are agreeing on that value at that point in time. I already said that all members must apply the operations in the same order. And in some of them, there's this concept of temporary leader, which all the systems we're exploring today are of one kind of distributed systems in which all the nodes are the same. There's no different kinds of nodes running different code. All the nodes run the same code. But in these kind of systems, and especially in Raft, temporarily a leader is selected, and he does some extra stuff, or all the nodes must send messages to him for a short period of time. Each member has a complete view of all the data. If the thing that one node or member knows, all the nodes in the system know. So there's no like partitioning or sharding going on here. Each member has a full view of the cluster. It knows about all the other members in the cluster, in the case of the cluster systems like Raft, Paxos, and SAB. But in distributed ledger technology or blockchain, since they have to scale to thousands or more nodes, they have to have a partial view of the other nodes. So that's how they differ. These kind of systems trade off consistency over scalability. So whenever they have to make a decision, they want to keep a consistent state over scaling. That's why we cannot have like consistent, infinitely scalable databases. That would be nice. But they prefer to be consistent over scalability. I think I have the wrong order of slides. So the natural predators for this kind of organisms, let's call them, are two, or the ones I could find. One is called Byzantine attack, or Byzantine fault tolerant, which is what happens if one of the nodes in the cluster, by error or accident or purposeful, sends weird message, corrupted messages, or tries to do something that it's not for the benefit of the cluster and for the benefit of advancing the state of the system. The cluster systems we mentioned, they cannot handle nodes misbehaving in the cluster. That's why I said that they run in a trusted environment. Another one is called, and the blockchain systems try to avoid this problem, and that's why we will explore what they do to solve it. And the civil attack is another problem, or another kind of attack or predator of this kind of system, which is the consensus on many of these systems is reached by voting, agreeing on a value by voting. But if you count the votes as one identity, one vote, a bot member can have more than one identity, present itself in the cluster as many nodes, and have more votes than one, and then try to make his view win over the others. This is solved. This is solved in the blockchain kind of systems by saying, okay, you want to look like many nodes, you will have to have the processing power of many nodes. Like to prove me that you are 10 nodes, you have to have the processing power of 10 nodes. So whenever you want to propose a value to be added at the next state, the set of operations to move the state forward, you have to prove me that you made a certain amount of work faster than any other members on the system. So then this is the proof of work, which is who is the member that proposes the next set of operations to be applied to the state is the one that can solve a hashing problem faster than the others. This means that there's a lot of processing and energy being used, and that's why other kind of consensus like proof of stake and proof of elapsed time are being explored. But this solves the Sybil attack and the Byzantine attack, because to do this kind of attacks, you have to have a lot of processing power. That means money, and you have to really think about the return of investment in the energy and hardware you need to make this attack. Another interesting property about blockchain is that even when I put them here in the consensus, strong consensus part, they have what I call, and I expect to be corrected on this, temporary rest conditions. Because as I said, when they are trying to agree on a value, the next set of operations to be applied to the state, everybody starts solving this problem and doing the processing. And what happens if two or more nodes find the solution at the same time? They gossip the next set of operations. So right now you have two new values to be applied to the blockchain in this case, two blocks to be appended to the blockchain. So what happens then is that you have to wait until one of the two, you have to keep a reference to all the potential next blocks until one of them becomes larger than the others. So you have to, if you really want to be sure that your operation was really applied and would stay in the main chain, you have to wait until your block is not the first one or the latest one. So it's like a temporary, like a trade-off for temporary rest conditions. What happens when a member joins on these kinds of systems? It has to synchronize the data from any of the other nodes, because since all the nodes have a complete view of the data of the system, they have to synchronize all the data to be active members of the group. What happens when a member leaves? Nothing, because since all the other nodes have all the data, there's no data to move around or anything. In the case that the node leaving is a leader election will happen to elect a new leader. Known specimens from these systems, I mentioned some already. Zookeeper that implements Zookeeper Atomic Broadcast, Raft that implements Raft. There's an Elixir implementation, React Ensemble, which implements Multipaxos, and in the case of blockchain, well, Bitcoin is in C++, but there are two blockchains in the Erlang ecosystem which have talks on the conference, Arweave, which the talks is next after this one, and Eternity, which was yesterday. And now let's do, since we are talking about zoos, let's see what nature has to tell us about distributed systems. So how do ants, which are all equal and really simple and a lot, solve a problem like building a bridge? They have a really simple distributed algorithm that you can check on the source, but basically it has like two rules. If you find a place that needs a bridge, you keep walking until there are no more ants, and keep walking. And if some ant starts walking above you, you stop until no more ants are walking above you. Then you continue. That's a simple solution, and it works. The other one is called in software ant colony optimization. The link explains the algorithm, but basically it's how ants organize to find food and communicate with others about the fact of where food is. What they do is when they go out of the nest, they start walking randomly until they either find food or find a trail. We will see what a trail is later. When they find food, they start walking straight back to the nest, and leaving a chemical trail. And when they go back to the nest, they say, there's food, follow the trail. And the other ants will start following the trail until they find food or not. If they find food, they will grab some food and go back and update and leave more chemicals on the trail. If they don't find food, they will just start walking randomly. And at some point, these chemicals will evaporate, so that if there was no more food at the end, the trail will disappear. The other case is when some ant is walking randomly and doesn't find food but finds a trail, it will throw a coin, let's say, and decide to follow the trail or not. And if it or she does, it goes in the direction of the food until she either finds the food or she doesn't, in which case it will start walking randomly again. This algorithm can be used to solve the traveling salesman in a really interesting way. The second kind of systems, I call them commutative consensus group or species. They don't have a cluster set of systems. The main solution that they are trying to solve is what happens when multiple agents are operating on copies of the same data, and then later they want to reconcile the changes and get the changes from the other systems. All of this started, I propose, you can correct me, with operational transformation in 1989, which was based on what happens if we are trying to collaboratively edit a document, like a text document or a text file. You might recognize this from stuff like Google Weave or Google Docs or Etherpad. Rest in peace, I think. It's no longer being maintained. But then later in 2011, an idea called commutative replicated data types was defined, which is a restricted set of data types with a restricted set of operations, which are commutative, which means you can apply it in any order and you will get the same end state, which is cool because if you're trying to scale a system to many, many nodes, you will be gossiping, and you don't want to do the consensus, the strong consensus style of let's everybody know about the next operation and then let's move forward. But you're just applying operations locally and gossiping the fact that you are doing changes and you're getting changes from others and you are applying them locally, knowing that no matter in the order that you apply the changes, you will converge to the same state at the end. A system is being developed in Erlang to try to define a programming language / platform to use these type of data types to build algorithms that scale. The core idea is that eventually, important, but deterministically, that's important too, they will converge to the same shared view. So eventually, because you're gossiping your changes and you're receiving changes in no particular order, but you know because of the properties of the data type that you will deterministically converge to the same state as any other node as long as you apply the same set of operations. It achieves this by restricting the operations you can apply and the kind of data types you can apply, of course. And since you can gossip the changes in any order and you can receive and apply the changes in any order, you can scale much more than the strong consensus algorithms or systems. It's a distant relative from the strong consensus systems in the sense that it wants to arrive to the same state and all the systems have all the data. But since it wants to scale further and its main preoccupation is not strong consistency, it uses different type of constraint and algorithms to achieve it. And I propose that blockchain or distributed ledger technology is a sibling of these two systems, because even when it wants to get strong consensus, at some point for the current set of new blocks, you have an eventually consistent view of the world. Each member has all the data. There's a case in LASP you can define filters. So you say, okay, whenever I'm receiving replication from other nodes, I want to ignore this, I don't care. So you can selectively not have all the data, but by default you have all the data. And the network view is either partial or full. This is because LASP, which is the system where you can use this right now, has many backends for distribution. And depending on the one you choose, you get different scalability properties. You can scale less or more. And this makes a difference in the case, if you're, for example, using the distributed Erlang backend, you have a full cluster membership view, but you can scale up to 70 or 100 nodes. And if you're using the Hyperview backend, you can scale to thousands of nodes, but you have a partial view of the membership because keeping a full view of many nodes is hard. They trade off scalability over consistency. They want to scale more. That's why they are eventually consistent. I tried to find a natural predator, and they are Amazon Web Service builds. One of the creators of LASP is Christopher Meiklejohn, and he's building a real system, and he's doing a PhD to design these kind of systems. And since he wants to test and benchmark the system running thousands of nodes, he has to initially set up a 1,000-node cluster, run the benchmark, stop it, and then pay Amazon Web Service for all the computers he's been using. So there's another predator, but it's not even a flaw. It's a property of the data structures. If you know about React and tombstones, if you are in a distributed system and you write a key and then delete it, and somebody else writes a key, you have to remember the fact that you deleted it and when, because when you are replicating the changes, if some other node says, I wrote this key, you have to remember that that key existed and was removed. Otherwise, old values may reappear out of nowhere. So these CRDTs have to remember when you remove stuff. So you may have an empty set that has a big state because you were adding and removing keys all the time. It's kind of a really slow attack where you use more memory on the system because it has to remember the past. What happens when a member joins? It's the same as the previous one. Since all the members have all the data, you have to synchronize, get the current state of the system. What happens when a member leaves? Nothing. There are no leaders, so you don't even have to make leader election. Known specimens of these kind of systems, LASP, as I mentioned, and since LASP uses CRDT, there's a project called LASP/types, which is a library with all the CRDTs that LASP uses implemented in Erlang. So there are like 30 or 35, so you can read about all of them, and they all have the same interface, so they are quite regular. Once you understand what each implements, it's easy to follow the other ones. And if you are on the web side of things, there's a library called AutoMerge, which implements a CRDT for the JSON data type. So if you know JSON, there are a set of operations you can apply to JSON that can be gossiped to multiple nodes. So for example, you can do the famous to-do app with a CRDT, and multiple users can be manipulating that to-do app in different computers and gossiping the changes between themselves, and eventually they will reach the same end state for the to-do list. To-do list can be a text editor, can be whatever, but another natural intermission. These are fireflies. Well, that's dark, but you may see the light. They are fireflies in Southeast Asia. And when they are together in groups at night, they synchronize. So they start flashing the lights at the same time. They have a really simple algorithm for that, which I find it similar to NTP in a sense, which is each firefly keeps track of a small subset of fireflies that are nearby. And whenever each firefly has an internal clock or timer, and when that timer runs out, it flashes. So if it's waiting and it sees some of the neighborhoods flashing, it will advance the timer forward, so next time it will flash closer to the other one. After a while, they will synchronize, and even you see like the limits of physics, because you will see that they flash in synchrony, but you see like a wave. In the old times in big concerts, you may see when they turn on the lighters, you will see the wave of lighters turning on to the back. So we humans are also distributed systems. The third one is the router group, which you might recognize more because I don't know when it started. But the first style is when you sharded a database and put a load balancer in the front, and based on the request, you decide to which shard or node to send that request. It was formalized and evolved with a Dynamo paper in 2007 from Amazon that described the Dynamo architecture. Then later in 2010, Orleans, a paper from Microsoft was described, which presents something called virtual actors, and that are similar. And this scales to big clusters, but I guess under 100 or a couple of hundreds. And at the internet scale, there's a set of papers that the 4 of them happened in the same year, 2001. I read this one core because I thought it was the one most similar to the others, but you can check the other ones too, which define, you may know BitTorrent or something like that, which is, or IPFS and stuff like that, which is a way to, at internet scale, to distribute load. In most of these cases, it's files, but processing or storing files, it's the same. It doesn't matter for the algorithm. The core idea of this kind of system is consistent hashing. Given a request, I have to consistently pick the member that will handle it, so that whenever I get more requests, they will be routed to the same member because he may keep some state out of it. Another idea is a routing table from 0 to log n hops. This means if you have a cluster and you connect to a node and say, I have this request, where should I go? If it happens to be that that node is the one that is the chosen one to handle your request, then you make zero hops. You are just there, and it processes your request. In the case of Orleans and Dynamo style architectures, since each node has a complete view of the cluster, they can tell you directly, I'm not the node, you should go there. So it's a one-hop routing table. And in the case of Core and CAN, since not all nodes have a full view of all the other members, what they can do is say, look, I don't have the value, but I don't know who has your value, but you should go there because he is closer to your problem. So at max, you will get log n hops, where n is the number of members on the cluster. This case is different from the previous two groups because different members handle different parts of the problem space. So you scale by specializing. Each node or member handles a subset of the whole problem space. That can be keys, data processing, or whatever. As I said, each member has a partial view of the data. And in the cluster case, they have a full view of the network, or the membership. And in the distributed hash table, they have a partial view of the membership because the scaling is bigger. They prefer scalability over consistency. REAC is an implementation of the Dynamo style architecture, and it's eventually consistent. The natural predator of this kind of system is Justin Bieber. So what happens if, also known as the hot key or hot replica or hot shard, is you are doing consistent hashing so that you make an even distribution of load among the members. But it happens that one key is Justin Bieber. And Justin Bieber is not any key. It's followed by many people. And every time he tweets, you have to distribute his tweet to everybody. And then everybody comes back and retweets. It's a mess. So this tweet is from 2010. And it says that Twitter had 3% of the infrastructure and complete racks of servers just to handle one key. So that's the main predator for this kind of systems. On membership join, when a member joins the cluster, you have to migrate to decide which slice of the problem space you will migrate to this system, because each member handles a slice. When a member leaves, if that member is the only owner of the slice and it just crashes, you will lose data. If you are shutting it down to put a new server, for example, you can temporarily migrate the data and then turn the other on and migrate the data back. Or you can do replication, which brings a new set of problems, which is whenever I do an operation on a member, I replicate that operation on 2 or n or w other members. So whenever a subset of the members die or leave, you still have the data or whatever you're holding. Known specimens for this kind of systems are RiaKV, which is implemented in Erlang and is open source, which is built on top of RiaCore, which is an implementation of the Dynamo style architecture, and it's also written in Erlang, and you can use it, and it's open source. And there's also Orleans, which is implemented in .NET, but there's an Erlang port called Orleans, which you can check there. And the last natural intermission is there's a mold that happens to like to eat oats. So if you put the mold at the center of the Petri dish, and then you place the oats in a way that mimics the cities around Tokyo, and you leave it there, it will spread and find the food, and then optimize the path back to minimize the amount of routes it uses to go and get the food and bring back the nutrients. And at the end, you will have a map that closely follows the railway system of Tokyo. So you don't need to have engineers to design a railway system. You just need a mold and some oat flakes, and you're done. And the last piece of advice from nature is starlings, which are a kind of bird that tend to fly together and have emergent behavior. And here they are flying in the shape of a bird, so I don't know if they are trying to tell us something or what. But they have a really interesting, the reason why they fly together is to avoid predators, so the falcon will try to hunt them, but if they are flying together, the falcon cannot follow one, so it gets confused and maybe it fails and gets tired and goes away. But he will try to cut some of the birds away from the flock, so that it can follow them. So it's in the bird's best interest to rejoin the cluster. So there you can see there how they fix a network partition. There's a small one there, but now it's a big one. You have a really big network partition going to happen right now. Wait, there. Rejoin, you have a cluster, and they did. The algorithm is explained in the source. It's similar to the Fireflies in the sense that each bird follows other 7 nearby birds, and it computes the average of the direction and speed and adjusts his speed or direction according to the surroundings, and you get a nice emergent behavior. So this was all, and I think we have time for questions or corrections. Thank you. Okay. No corrections?
How many papers did you read into making this talk?
So the question is, how many papers did I read? In the last 2 months, around 10. But 2 years ago, I had a really bad idea. I don't know if you know about Adrian Collier, which writes a paper a day. And when I saw that and I was following him, I said, he's crazy. Let's see how hard it is to read 5 papers a week. So I did that for like 3 or 4 months, and I read like 60 papers, I don't know, too many to count. But the difference is that I wasn't writing the blog post. I was just highlighting them and keeping them. I have like a pile of papers like this. But I was just following interest. In terms of distributed systems, to get this knowledge, reading the seminal papers and all of this, you may have to read less than 20 papers, which at 12 pages per paper is a medium-sized book. They are really like dense, so you may need to read it more than once, but it's really efficient. Instead of writing blog posts or following Hacker News, go to the source and read what they have to say. Follow them on Twitter, watch their talks, search on YouTube. They will present the paper in 1-hour talks, so it's easier to follow with diagrams and stuff like that. So it's doable. It takes time, but at some point you get up to date. So you are following papers from the last couple of years. So it gets slower, which is cool, because if you have one paper every week or every other week, you can follow them in a natural timing.
I have a question. influence of some of the core ideas, kind of back before the popularity of the internet, like the Lamport clocks time paper or Hewitt's actors?
Yeah. I think it's common to all of these systems where they follow asynchronous message passing, which can be CSP or actor-style asynchronous message passing, which is basically Erlang, and a kind of actor model where I said member is a generic term I use because you have different types of members. Some are hardware nodes, some are virtual nodes where you have more than one node per physical computer. So almost all of them are object-oriented in this sense, where you have like a thread of execution with some internal state that communicates with the rest of the members through asynchronous message passing. So in that sense, it's almost like the actor model or object orientation done right at the internet scale, or at least at cluster scale. So they are common in that sense. If you read CSP or read Alan Kay talking about object orientation or read the actor model stuff from the 80s, you start to see that the actor model and object orientation and the internet are kind of the same architectural pattern. Because if you see a server as an actor and you see an HTTP request as a message, it will be like a gen server call in this case because it will reply instantly, then you are seeing the actor model at internet scale. And as you know, the internet cannot move in lockstep to be consistent, so the internet is the biggest object-oriented or actor model system there is. So there's an interesting, but I don't know if there's this PhD thesis that defines REST, the representational state transfer, that is like a condensation of what the author learned by being involved in the development of the web, which defines how the internet works, and people took the REST style from there. And that's an interesting, but it's a PhD thesis, so it's like 80 pages or something like that, but it's really useful, and even it's useful for doing web stuff even. You learn about how to scale the internet, but you also learn how to build APIs that scale, so it works in the distributed systems and in your web day-to-day job.
All right, thank you very much.
Oh.
There's one more question. Yes.
Going back to Joe's talk from this morning, is there any paper that you've read in the last few years that you think is kind of underappreciated?
All. How many of you here read at least one of the papers? Whoa. I don't know why I'm up here speaking. Well, for the cameras, it was like 70%. I personally like the papers that are, I'm an engineer and I build stuff for a living, so I like the ones that are in between academia and applied engineering. So the Dynamo paper, the Orleans papers are great. But yeah, and well, the Raft paper is great in the sense that consensus algorithms seem scary, but it's explained in a way that it's really approachable. So what I would say is, people tend to think that papers are for PhDs, and some of them are not. Some of them they are, like Paxos and the vector clock papers. I've read the 3 biggest ones 2 times, and I'm still trying to understand them. Would you?
Yeah, I've got a question. I really love what you did here.
Thank you.
Everyone here is working in distributed systems, whether they want to or not. But there's 2 different categories I think that might fall into: system implementers and people who are using systems.
Yeah.
One of the things that I really loved about this talk is you're taking an approach to try to categorize some of the behaviors and properties of the various systems that either if we're not working on, we're probably going to be using in our job in one way or another.
Yeah.
And it's simply unreasonable, I think, to expect every industry practitioner who's not implementing the systems to be completely familiar with all of the literature.
Yeah.
And even if you are, that's still a tall task. So I was wondering, in the work that you did preparing for this talk, if do you have any ideas as to how an industry we could maybe better disseminate some of this information without having to go to the first principles?
That's a great summary. I forgot to summarize it like that. But a summary for the camera also for everybody else is, I mentioned it shortly at the beginning, like when you're evaluating programming languages and when you're evaluating databases, you have, even if you start with the problem you have, we have categories and a vocabulary and like to compare them. I can tell you key value store or document-based or relational or columnar, and if you are even if you are not following papers, you can understand easily what they mean and what's the kind of problems that they solve and what are the weaknesses and the trade-offs they have. So somebody comes and say, okay, I have to solve this problem, and he explains or she explains what the problem is and what the trade-offs are. And we can talk about programming languages and databases, like, okay, these are the trade-offs, these are the properties, this is related to this is related to that, this doesn't work in this case. What I tried here is to try to categorize or to define a set of categories or vocabulary to talk about distributed systems without going to read the papers, because it's hard. But I found like 3 or 4, like I managed to group them in 2 big groups and 1 distributed in 2 smaller groups, and some categories like core ideas, data, cluster membership, scalability. But I don't know if they are the right ones, but I think we should keep trying to categorize them and make a map of the territory and see which map is the best, the one that shows the territory better, which I don't know if this is, but.
I'm afraid that's all the